Okay. So I think that the talk about the warm physics is no problem in this workshop. So I'll talk about especially general wormhole and the dynamic wormhole, and I introduced several wormhole models with the scalar field and the cosmological models. And the last part is some quantization strategies about Lorentz wormholes according to the municipal space models. In general, the wormhole is defined like this. It requires a non-zero minimum size of R, and it also requires the two asymptotically flat regions. But here I put the question mark. It means that later I show you the cosmological model with the wormhole case. In this case, it is not flat, asymptotic flat in any way, and there is no horizon because it is possible to the two-way travel on both sides, and this wormhole model also satisfies the Einstein field equations. From the general model, this requires the minimum neck. So from here, through the several constraints and the calculations, then we can see that some constraints about some methods. It means that the energy condition is violated. So the method which constructing the wormhole is so-called exotic method. And the result in the case of a dynamic wormhole is the same as the former non-dynamic case. In the dynamic case, has some null hypersurface has a special time coordinate, and also there is some constraints about this geometry. Here, the A means the area of the surface. So this last condition means that the minimum size of the cross-section area. So from here, with this, and we using the Ray-Choudhury equation for the null geodesic through the wormhole. Then from this equation we can show these relations. So these relations means that just a violation of null energy condition. So it also requires the exotic method to constructing the wormhole. Now I show you some wormhole models. The first one is the Morris-Thorne type wormhole. It is very simple type. As here, the phi is the left function, and B is the wormhole shape function. So if we put some form of the function of BR, then we can set up the wormhole model. And the second one is the Visa type wormhole. Visa type wormhole is the very simplest one. It takes the ordinary Schwarzschild coordinate and take two copies of the two Schwarzschild type, and then remove the cut just outside of the event horizon. Then identify these two Schwarzschild geometry. Then this operation is some kind of surgical operation. So we call it Visa type wormhole. Later, Visa extends to his model into the horizontal some case or various kinds of wormhole examples. The most simplest one is that just take the Minkowski spacetime, not such a Schwarzschild type. Just take the Minkowski spacetime and cut two balls. Of course, the two balls are very far each other, and then identify these two balls. Then it is the simplest wormhole. You can see some kind of this type of This is the figures for the simplest wormhole. In the Minkowski spacetime, we cut the two balls and identify these two balls. And if someone go into the mouth of this wormhole and he came out. Another figures for this model is this one. I copied this figure from the Gibson's book entitled The Warped Spacetime and the Black Hole. So in this case, it is Gibson and his wife. For example, if they are separated by the few light years, then they can hold their hands each other. They shake their hands. Even though there are many results about the wormhole researches, but now I show you some my recent results about the wormhole physics. The first one is that wormhole in cosmological model. It was published in '96. I took just a simple type of the metric element. This metric element denotes the wormhole in Friedmann-Robertson-Walker universe. It is very simple because in the universe there is only one wormhole in the center. From here, I can say that Einstein's equations, and also I can introduce some several parts for the matter part. The rho is energy density, and tension, and energy flow, and pressure. The main result of this research was like this. Here is some test for the matter constructing the wormhole is exotic or not. If it is positive, then the matter, that power rho, exotic, but if it is negative, then it is not exotic. In the case of the cosmological model with wormhole, this parameter is calculated like this. There are two parts. The first part is a cosmological part, calculated from the scale factor R, and the second part is just calculated from the wormhole spacetime. But when you see only the second part, then it is just a positive one. But if we think at the early stage of the universe, then we can make this the negative one. So then we can make this parameter can be negative for the very early times. So in this case, the matter can be not exotic. I mean that we can make wormhole without using the exotic matter in the very early stage of the universe. From here, I also obtained some solutions about the matters and some solutions about cosmology. This is the solutions for the case of metals. And the second one is the warmer is the scalar field case. It was published the last year with Sensor Kim. The first case is warmer with minimally coupled matrix scalar field case. This is the Lagrangian for the scalar field, and the math part of the scalar field. And here the Einstein's field equation for this model. If we define the right-hand side is the, I'm sorry. Okay. If we define the right-hand side as the effective matter part, then we can find some solutions for this matter. And also, this was the, we can check the exotic property for this case. My main purpose for this model is that the question is that is it possible to make warmer with using non-exotic matter for the case of scalar field. So I tried the first case of the minimally coupled case, but in vain. I mean that the scalar field cannot change the sign. So here the matter is still exotic. Here is also the solutions for the matters and the scalar field. At the second step, I also tried to make the model with the massive scalar field case. Here also, we cannot change the sign with this scalar field. As we know that the massive scalar field violates the strong energy condition, but it does not violate the null energy condition. I mean that the method constructing the wormhole should violate the null energy condition. So now finally, the third step is the wormhole with the general field, general scalar field. From here, we can see the exotic properties for this model. Is very long lines. So if we think just near the case of wormhole's throat, the equation is simplified like this. Then from here, if here the psi is the coupling constant and m is the mass of the scalar field, and B is the size of the wormhole's neck, and phi is the scalar field. So if the mass or the scalar field is very large, then we can make this term into the positive, even though tau minus rho is negative. So conclusion for this model is that we can make the wormhole with non-exotic matter in the case of generally coupled scalar field case. But the more interesting thing in this model is that we tried to find the solution for this model. The field equation for this scalar field is like this. There is some asymptotic solutions, but here, if we change the coordinate, the R into the S with a relation like this, then the equation for the scalar field is just the Schrödinger type. So from here, for the very special, from here, the potential is some bounded model. For the case of a special type of wormhole, then the equation is like this. So for the small parameter S, it means that just near the throat, it can be changed into just a harmonic oscillator problem. So as you know that the solution for this model is the harmonic polynomial, and that the lambda is 2n plus 1. It means that MB0 is given like this. It means that minimum size of the wormhole B0 should be quantized for the case of non-minimal positive coupling case. The last trial for my research on the wormhole is just some quantization problem for the Lorentzian wormhole. But frankly speaking, that it is not finished yet. In any case, I tried to show my recent result. Just as you have seen that, you see my cosmological model with wormholes. And a few years ago, before my work, then Paul Tom Roman write a similar paper in the case of inflationary model with the wormhole case. So I think that we need some before the inflation era. So I mean that the Planckian era. In this era, we need some the quantization schemes. For the simplest one is the using the fluidity equation. So here I tried the gravitational action for this model, and this is the exchange curvature for the calculation of the actions, and this is shift vectors. But at first, I tried to the case of just wormhole models, just a moisture zone type wormhole. Sorry. Yes. Yeah. The first case is just the moisture zone type wormhole without any scalar field or any cosmological models. That here, but I put into the time evolution part into the BR with some dependencies on R. Then in this case, the time part is only in the RR part. So here, so the time dependency is only in HRR. So there's no NI terms. The action, gravitation action, in this gravitation action, the first and the second term is eliminated each other. So there is no time derivative term. In this case, it means that the dynamics for the wormhole doesn't have any meaning for the wormhole in flat space-time case. we cannot find any momentum for the wormhole. Next, we try on the wormhole in the cosmological models, which was shown a few minutes ago. And here tried only the case of the curvature is k equals 1 in the cosmological model. The reason is that if we use the k equals 0 or k equals minus 1, it means that open or applied universe case, then the spatial integration should be diverse. And also, we put the shape of the wormhole is dependencies of 1 over r. Then we try the degrees of freedom is scale factor and wormhole throat size. In the case, I can calculate the scalar curvature like 4 terms. So next step is the spatial integration to find the last term. But the third term has some divergences. So I think that the reason is that just the curvature is similar to the open universe, because around the wormhole there is some Lobachevsky style curvatures. So at the last step, I'm thinking only that some moving wormhole space-time with the Hubble expansion. The dependence of the wormhole and the scale factor is given at my former work. So it means that when the scale factor increase, I mean that the cosmology expands, then size of the wormhole. In the wormhole also they expand with the same rate. So in this case, we can see the only degree of freedom is the scale factor of r. It's very similar to the case of quantum cosmology for already achieved by the Vilenkin, Hartle, Hawking, others. So in this case, I make the Lagrangian like this. The only difference is the coefficients of the scale factor of r. The minimum size of wormhole B0 is put into the like this. So from here we can make the field equations and the potential. So from here I show you the some results for this one. From the field equation, if we choose the factor ordering the parameter A is equal to 0, then the potential is given like this. The dotted line is just the cosmological model without the wormhole. So the potential is shrinked with the wormhole. In any case, if the point 0, r equals 0, means stuck in the 0 position, but in the quantum level, we can take out, or we can expand this universe with some tunneling probability. The probability is given like this with Euclidean actions. And also, we can calculate some wave function for this model. From here, we can change the wave function for the wormhole also, because we already know the relations between the R and B. From here, we can obtain the expectation values of the minimum size of wormholes. But the second case is that here, it means that alpha square is defined as the coefficient of the scale factor of R. So if the minimum size of wormhole is greater than 3/2, then the alpha scale can be the negative. The potential is given like this. In this case, all regions are classically allowed, so we can calculate we can obtain the wave functions with using a WKB method. When the factorial parameter is equal to 1, the fluidity equation is given as like this, and the solution to this equation is some linear combination of the area functions. But the wormhole effect is here, the alpha squares. So with some special boundary conditions. For example, at the origin, if the wave function should be 0, then it looks like the Blanky type of cosmological models. And if there is no boundary condition, then it is just hard-working type wave functions. So this is some simplified figures for these models. This is the potential of this equation, and this is a hard-working type of solution. I mean the area function, and the other two dotted line is for the zero boundary conditions, like the Blanky type. So now I'll summary and the discussions of my works. The summary is just about my last work. I mean that the quantization of the wormhole. The first result is that in the just wormhole without any scalar field or without any cosmology, then there is non-dynamic result in quantum level. So in this case, we cannot calculate any municipal space models for this wormhole. And next one is we tried some non-comoving wormhole with the Hubble flow. But in this case, we experienced the divergence effect during the spatial integration. And the third trial is comoving wormhole with the Hubble flow. So the result is just a simple modification from the quantum cosmological model. It is relevant. So afterwards, I'll try to the case of some more general model. It means that I tried only simple model with the simple type of wormhole function. So I can change the wormhole function into the other type. So we can try the other type of models, and we can also the result with the Bisters type wormhole. Thank you.